Hello, everyone, and welcome to Educlynk. I'm Mr. Com, your chemistry teacher, and today we're going to handle mole concept. So, in fact, this is the module one, the matter and transformation, the chapter, the mole concept, the lessons. In lesson one, we're going to have the notion of the mole. Lesson two, percentages, composition, empirical and molecular formula. Lesson three, we're going to see the mole concept and gases. Lesson 4, the mole concept and solutions. Lesson 5, the mole concept and balance equation. So lastly, we are going to see titration. Titration that involve acid-base titration, redox titration, precipitation titration. So we'll go straight to the point. Lesson 1 is the notion of the mole. So the mole of a substance is that amount of substance that contains as many elementary particles as there are atoms, exactly 12 grams of carbon-12 isotope. Mathematically, the mole of a substance is given by small n equals to given mass all over the molar mass. What small m is the given mass, and capital M is the molar mass. Molar mass. Let's take an example. So let's take a small example. Example 1. Example 1. Calculate the number of moles contained in 4 grams of sodium hydroxide. The data have been given to us as data. Gram. That of sodium, molar mass 23. Hydrogen, molar mass 1. Oxygen, the molar mass 16. Okay. The mole of a substance, small n, is equal to given mass by the molar mass. The given mass have been given to us as 4 grams. Molar mass, we don't know the molar mass. We have to calculate. So, the molar mass, mR, we don't know. The given mass is 4 grams. So, the unknown is the molar mass that we don't know. But our molar mass is given by sodium. The molar mass is 23. 23 times the number of sodium in the compound is 1 plus oxygen, the gram is 16. Oxygen gram is 16 times the number of oxygen atom is 1. Hydrogen, the gram is 1. The number of hydrogen atom is 1. So the molar mass mR is equals to 40 gram per mole, such that 23 times 1 is 23, 16 times 1 is 16, 1 times 1 is 1. The molar mass is a sum. We apply our formula. Number mole equals to given mass 4 grams divided by the molar mass 40 gram per mole. Gram cancel. The number of mole small n equals to 0.1 mole. So we are going to go straight to example 2. Example 2. Example 2. Example 2. Calculate the number of moles in 13.2 grams of ammonium sulfate. So realize that in the question we have our given mass, the given mass 13.2 grams. Molar mass once more is unknown. So in the table of value or in the data, I have to add some data, knowing that oxygen will have oxygen, molar mass. Nitrogen we don't have. So we're going to give you nitrogen, 14. Sulfur, 32. So example 2 is similar to example 1. Example 2 says calculate the number of moles in 13.2 grams of ammonium sulfate. So we'll go for get safely. So once more we'll have our given mass 18.2. Molar mass we don't know. But the formula says number of mole is given mass over the molar mass. Molar mass equals to this 2 is multiplying nitrogen, multiplying hydrogen. So I put a bracket. So 2 bracket open. Molar mass for nitrogen is 14. So having 14 times the number of nitrogen in the compound. We just have 1 nitrogen in the compound. So times 1 plus the molar mass for hydrogen is 1. So having 1 times the number of hydrogen, which is 4. All that bracket plus sulfur molar mass is 32. 32 times number of sulfur 1 plus we're left just with the atom of oxygen. So oxygen molar mass 16 times 4. So if you add them up, molar mass is 132 grams per mole. Applying the formula, number of moles is given mass 13.2. However, molar mass 132. Automatically, so here's gram per mole. Gram cancel. Automatically, number of mole is punch 13.2 divided by 132. So number of mole is 0.1 mole. So that is the notion of the mole. What you have to memorize or retain is that the number of mole is given by given mass over the molar mass. So we can make given mass the subject of a formula. Using the formula N equals to given mass all over the molar mass. If we cross multiply, we're going to realize that the given mass more M is the number of moles N times the molar mass. So that's the given mass. You can also make MR, which is the molar mass, subject of the formula. So MR is also equals to the given mass out of the number of moles. So actually there are 3 formulae as far as the notion of the mole is concerned. We have the pioneer formula or the mother formula, which is number of mole, given mass or the molar mass. We have our second formula, which is the given mass is the number of mole times the molar mass. The molar mass MR is a given mass divided by the number of moles. So we're going to go to lesson 2. Lesson 2 is the percentage, composition, empirical, and molecular formula. So we'll go straight to lesson 2. Music. So lesson two. Lesson two. Or still lesson one. Still lesson one. Still lesson one. Notion of mole. Notion of mole, still lesson one. We're done with lesson two. So we're going to see the Avogadro's number. The Avogadro's number. The Avogadro's number is defined as the number of particles contained in 1 mole of a substance. So the Avogadro's number will have Avogadro's constant. So the Avogadro's constant L equals to 6.02 times 10 to the 23 mole minus 1. So here we're going to see how we can calculate the number of particles contained in matter. So the number of particles contained in matter is given by capital N is equals to small n times L. We're just from seeing how to calculate small n. Small n, remember, is the given mass over the molar mass. But small n is the given mass over the molar mass. So n, capital N, is given mass, molar mass, times N. So here we can note M is the number of particles. Number of particles. Mr, the molar mass. Small m, the given mass. And L is 6.02 times 10 to the 23 mole minus 1. So in order to calculate the number of particles, the number of particles here can be ions, molecules, particles, electrons, protons. That is represented by capital N. So capital N is small n times L. Where small n is the number of mole, is a given mass by the molar mass. So automatically our capital N equals to given mass, molar mass times L. Then we'll have an example where we can calculate the number of particles. So example. Let's see. Example 1. Calculate the number of ions, the number of sodium ions, in number of sodium ions in 10.4 grams, 4 grams of sodium hydroxide. Calculate the number of sodium ions in 4 grams of sodium hydroxide. So together the data, L equals 6.02 times 10 to the power 23 mole minus 1. So that's example 1. Example 1 is telling us calculate the number of sodium ions in 4 grams of sodium hydroxide. So I have to calculate. So Let's apply the formula. Capital N equals to, so here is the solution. So solution, capital N equals to small n times L. So I have to calculate the number of moles. But number of moles is giving mass over the molar mass. Number of moles is giving mass 4 grams. Molar mass 40 grams per mole. Sodium hydroxide. We calculated the molar mass of sodium hydroxide in the first size. So sodium hydroxide molar mass is 40. For repetition, how do we get 40? Sodium, remember, it was 23. Plus oxygen is 16. Plus hydrogen is 1. So our number of mole N equals to 0.1 mole. But remember, in this case, we're calculating the number of sodium ions in sodium hydroxide. We ionize our compound. Sodium hydroxide dissociate to give sodium plus OH minus. Our number of mole with respect to the OH with respect to sodium plus, because the question is saying calculate the number of sodium ions. In this case, there's only one sodium ion in the compound. So we multiply 1 times 0.1. Number of mole is still 0.1 mole. So apply the formula, capital N equals to small n 0.1 times Avogadro's number. The Avogadro's number is 6.02 times 10 to the power 23. So n equals to 6.02 times 10 to the power 22 ions. So let me brief this solution. The solution is, or the question is asking us, calculate the number of sodium ions in 4 grams of sodium hydroxide. It gave us the Avogadro's number. So small capital N is small n times L. So but small n, which is the number of mole. The number of mole is giving mass by the molar mass. So number of mole is 4 grams. Divided by 40 grams per mole. The one of sodium hydroxide. So N is 0.1 mole. So N equals to 1. 1 because sodium, there's 1 sodium ion. So it's 1 times 0.1, which is 0.1 moles. So go to example 2 in calculating number of particles. Example 2. Example 2. Calculate the number of carbon dioxide molecule in 4.4 grams of CO2. They gave the Avogadro's number as 6.02 times 10 to the power 23 mole minus 1. That's example 2. So we apply the formula for the number of particles. The number of particles, capital N equals to small n times L. So automatically here we have to calculate small n. But small n is giving mass all over the molar mass. Giving mass is 4.4 grams. Molar mass we have to calculate. Carbon, so I have to give you data. Gram. Carbon is 12, oxygen is 16. The molar mass. So having carbon, there's 1 carbon, so it's 12 times 1 plus oxygen is 16. The RAM is 16. So molar mass for carbon dioxide is 44 gram per mole. This implies the number of particles is, or less the number of mole first of all. The number of mole is 4.4 grams divided by 44 gram per mole. Can cancel. Number of mole equals to 0.1 mole. So we have our number of mole, and the formula is telling us small n is capital N, which is the number of molecule, is small n times L. So there are two ingredients. There's a number of mole and there's L. So apply the formula knowing that we already have the number of mole. Number of mole, which is 0.1 mole. So the number of molecule in this case is 0.1 times 6.02 times 10 to the 23. So the number of molecule is 6.02 times 10 to the power 22. Now is molecule. So what is the difference between example 1 and example 2? In example 1, we're dealing with an ionic compound. So we're dealing with sodium hydroxide. So, but here we're dealing with a covalent compound. So no need to ionize a covalent compound. So can't ionize a covalent compound. That is why the number of molecules is just N times L. Whereas the number of ions, we have to multiply the number of ions by the number of moles. So going to example 3. Example 3, we are going to go to a more complex exercise. So example 3. Example 3. Calculate the mass. So example 3. Calculate the mass of carbon dioxide in 6.02 times 10 to the power 22 molecules of CO2. Calculate the mass of CO2 in 6.02 times 10 to the 22 molecules of CO2. So in this case, we have been given instead the number of particles. Then we have now to calculate the mass of CO2. So let's apply the formula. So capital N is a solution. Capital N equals small n times L. L is the Avogadro's number. So L is the Avogadro's number. So we apply the formula, but small n is giving mass all over the molar mass. We substitute this formula in this equation because remember, we're looking for the mass small n. So capital N equals to giving mass, molar mass times n. We make small m subject of the formula. So small m equals to cross multiply. So cross multiply, you are going to have capital N times m r divided by L. So in this case, our mass will be equals to capital N have been given to us in the question. This is it here. 6.02 times 10 to the power 22 times molar mass for CO2. We calculate the molar mass for CO2. You know that the molar mass for CO2 CO2 is equals 44. So times 44. All that divided by the Avogadro's number, 6.02 times 10 to the power 23. So our mass will be equals to 4.4 grams. So if you punch, take a calculator, you punch 6.02 times 10 to the 22 divided by 6.02 times 10 to the 23 times 44. So answer will be 4.4 grams. Okay, we're going to go straight to lesson 2. Lesson 2 is the percentage composition, the empirical formula, and the molecular formula. So lesson 2. Lesson 2. Lesson 2 is divided into 2 parts. There's also percentage composition. So Roman 1, percentage composition. Percentage composition. Percentage composition. So we're going to use the formula for percentage composition. So the percentage composition of an element in a compound is given by, let's say the element is X. So let's say a compound, then inside a compound we have X element. So percentage of X equals to the number of X times the gram of X divided by the gram of the compound times 100 on 1. So N stands for the number, so not the number of moles. So let's take a typical example. So let's take a typical example. From the formula, we are going to the formula we are going to go straight to an example. Example 1. Calculate the percentage composition. Calculate the percentage composition of calcium, carbon, and oxygen in calcium carbonate. So that's example 1. Calculate the percentage composition of calcium, carbon, and oxygen in the compound calcium carbonate. So to calculate this one, we are going to start by determining the molar mass of the compound. So there's some data. So RAM. Calcium is 40, carbon is 12, oxygen is 16. Okay. So let's calculate the RAM now. So RAM molar mass equals to, there's one calcium atom. So having calcium, the molar mass is 40. So having 40 times the number of calcium, which is 1, plus carbon. So there's carbon, there's 1 carbon, which is 12. The molar mass is 12 for carbon. There's 1 carbon atom, plus oxygen atom. So oxygen is 16, molar mass 16, times 3. Mr equals to 100 gram per mole. So we have to calculate the percentage of calcium inside calcium carbonate. So percentage of calcium equals to, remember, the RAM for calcium is 40. So it's 40 for calcium times the number of calcium atoms. There's one calcium atom in the compound times one calcium divided by the sum, the MR, divided by the sum. The molar mass, which is 100, divided by molar mass 100 times 100 because we're calculating percentages out of 1. Percentage of calcium equals to 40%. Percentage of calcium equals to 40%. So let's calculate now the percentage of carbon. So percentage of carbon equals to, so carbon, the RAM for carbon is 12. So I mean 12 times the number of carbon atom. So carbon is 1, the RAM for carbon is 1. So carbon is 1. All that divided by the total boundary times 100 all over 1. Percentage of carbon equals to 12%. So we have to calculate also the percentage of oxygen in the compound. Percentage of oxygen. Because we have already calculated the one of calcium, carbon. We're left with oxygen now. Calculate. So percentage of O equals to, in this case, oxygen is 16. So I mean oxygen 16 times the number of oxygen, which is 3. 3 oxygen atom. 3 oxygen divided by the RAM, 100 times 100 all over 1. Percentage of O equals 8%. So that's all about example 1. So go straight to example 2. Example 2 is a more complex exercise compared to example 1. So you can take example 2. Example 2. Calculate the percentage composition of carbon, hydrogen, and oxygen in glucose. Glucose, the formula for glucose is C6H12O6. Calculate the percentage composition of carbon, hydrogen, and oxygen in glucose. So that's the formula for glucose. So the first step to do is to calculate the molar mass of the compound. So the molar mass of the compound, MR, so I have to give you some data. So let's take carbon to be 12, hydrogen to be 1, oxygen to be 16. So here are the relative atomic masses. So calculating the RAM of the compound, so RAM of the compound equals to, so RAM for carbon is 12. So carbon is 12 times the number of carbon atom is 6 with 12 times 6 plus hydrogen. Hydrogen, the RAM is 1, so RAM 1 for hydrogen times 4 plus oxygen. RAM of oxygen is 16. I mean 16 times 6. So molar mass equals to 180 grams per mole. So we have to calculate the percentage of carbon, hydrogen, and oxygen. So go straight to the point. Percentage of carbon equals to. In this case, the gram for carbon is 12. So gram of carbon is 12. 12 times. So the gram of carbon is 12 times the number of carbon atom. So it's 6. 6 divided by 180. So 180 here is the gram of the compound. That means the summation, the mass of the compound times 100 all over 1. Percentage of C equals to 40%. So percentage of H now. Percentage of H equals to. In this case, the ram for H is 1. So having 1 H times the number of H atoms. So having 12H times 12H all over 180 times 400 all over 1. Percentage of H equals to 6.6%. 6.6%. In fact, 6.66. We can take 6.6%. So, percentage of O equals to. So, oxygen now, the ram for oxygen is 16. So, 16 times 6 all over 180 times 100 all over 1. So, percentage of O equals to 54.4%. 54.4%. 54.4%. So that's the percentages on the board. Percentage of O, percentage of O is given. Percentage of H is given. Percentage of C is given. As I told you earlier, we said our lesson 2 is divided into 2. The percentage composition, empirical and molecular formula. So empirical and molecular formula. So let's go to the second part of lesson 2. The second part of lesson 2. Second part of lesson 2. Part 2 of lesson 2 is talking about, so let's say part 2, the empirical and molecular formula. So we have a formula linking the two, the empirical and molecular formula. The empirical formula is a formula that shows the simplest ratio of elements inside the compound. The molecular formula shows the actual number of each element in the compound. So I repeat, the empirical formula shows the simplest ratio of elements in the compound, while the molecular formula shows the actual number of atoms in the compound. So the empirical formula, the molecular formula, equals to N into empirical formula. So where N stands for the number of moles. So this is the pioneer formula. The pioneer formula. So let's take an example. Example 1. Example 1. An organic compound. An organic compound. So let's see example 1. An organic compound contains 40% carbon 6.66% hydrogen and 53.4% oxygen. Full stop. The molar mass, the molar mass of the compound, the molar mass of the compound is 108. So that's a typical exam question. An organic compound contains 40% carbon, 6.66% hydrogen, and 53.4% oxygen. They gave us the molar mass of the compound, which is 108. So step one means we are going to identify the elements present in the compound. So remove the various elements. The elements will have carbon, hydrogen, and oxygen. So the percentage for carbon is 40. Percentage of hydrogen is 6.66. Percentage of oxygen is 53.4%. We divide. I have some data that I have to give you. Data. Take carbon to be 12, oxygen to be 16, hydrogen to be 1 as relative atomic masses. So carbon is 12. Hydrogen is 1. You divide by their molar masses. So divide the percentages by their molar masses. So you do the division. Oxygen is 16. Here it's going to give us 3.3, 6.66, 3.3 also. We divide by the smallest 3.3, 3.3. We divide by the smallest. Here we have 1. Here we have 2. Here we have 1. So these numbers are gotten as a result of the division. So we divide these numbers that you have gotten as a result of this division. Because 14 divided by 12 is 3.3. 6.60 divided by 1 is 6.66. 53.4 divided by 16 is 3.3. You divide by the smallest. The smallest in this case is 3.3. So the masses are, or the ratios are 1:2:3. The empirical formula equals to CH2O. That's the empirical formula. CH2O. Carbon is 1 carbon. Hydrogen is 2. Oxygen is also 1. So that's the empirical formula that we calculated. We have to calculate now the molecular formula, because that's the first step. The first step is empirical formula. Second step, molecular formula. So go to calculate molecular formula. The molecular formula. So the molecular formula. Molecular formula. The molecular formula. In this case, we know our empirical formula, or we know the pioneer formula. N into empirical formula equals molecular formula. So N is a multiple. So if you know the multiple, you automatically know the molecular formula. So let's use the N into the empirical formula is CH2O equals to the mass of the compound. So from the question, we realize that the mass has been given to us. So mass has been given to us as 108. For carbon, the gram for carbon is 12. So it's going to be N into 12 plus 2. 2 for hydrogen. Because hydrogen is 1 times 2 is 2. oxygen is 16 times 1, 16. Sorry, this is equals to 180. So 30 N equals to, because 12 plus 2 is 14, plus 16 is 30, equals to 180. So N equals to 180. N equals to 180 divided by 30. N equals to, N in this case is 6. So knowing that we know N, we apply the formula N into empirical formula equals to molecular formula. So apply the formula. So N into empirical formula equals to molecular formula. N is 6, so 6 into CH2O equals MF. MF here is a molecular formula. So open the bracket. So having C6H 2 times 6 is 12 O6. That's the molecular formula of the compound. So we can also determine the molecular formula of a compound using the combustion method. So let's see how we can determine the combustion method. Let's use the combustion method. So let's see. It's the definition of MF and EF using the combustion method. Combustion method. So in this case, I'm going to give you some tips in order to determine the masses of carbon, hydrogen, and oxygen. So, due to the combustion of any organic compound, two products are formed. There's carbon dioxide and there's water. So you have to know the mass of carbon in carbon dioxide, the mass of hydrogen in water. So the mass of carbon equals to 12 out of 44 times mass of CO2. Because 12 is the mass of carbon, 44 is the mass of CO2. So the mass of hydrogen is 2 over 18 times the mass of water. So mass of oxygen is mass of the compound minus mass of C plus mass of H. So having the various masses, you can go straight to the determination of the empirical formula. Because in most cases, this method is used in order to determine the empirical formula for organic compounds. Because whenever organic compound burn, there are two compound form. That is CO2 and water is from also. So in carbon dioxide, we have to know the mass of carbon present in carbon dioxide. Also in water, we have to know the mass of hydrogen present in water. So once you know the mass of carbon and hydrogen, you have to now calculate the mass of oxygen in the compound, knowing that the element contain or the compound contain carbon, hydrogen and oxygen. I know also the whole mass of the compound. So the mass of O is simply the mass of compound minus mass of C plus mass of H. So we can go now to lesson 3 or the second part of lesson 2. No, look at lesson 3. The mole concept and gases. So go to the mole concept and gases. the mole concept and gases. Lesson 3, the mole concept and gases. The mole concept and gases, we are going to see the ideal gas equation. Ideal gas equation. The ideal gas equation is a combination of two laws, Boyle's law and Charles' law. So Boyle's law states that the pressure is inversely proportional to the volume, such that P is equal to K on V. When I remove the constant of proportionality and include K, K is a constant, making K the subject of the formula K is equal to PV. So that's our first equation. I call it equation 1. Then using Charles' law, because this is Boyle's law. Yes. Using Charles' law is saying that the volume is directly proportional to the temperature. So Charles' law, V is equal to KT. V is equal to, or K is equal to V all over T. That's equation 2. So that is Boyle's law, and here is Charles' law. So these two laws can be combined to form the combined gas equation. So the combined gas equation is P1 V1 over T1 equals to P2 V2 over T2. So this final equation is a combination, Charles' law and Boyle's law. So we have the final equation. Then our point of focus at the advanced level here is the ideal gas equation. The ideal gas equation that is linking Boyle's law, Charles' law, and the Gale-Lussac law. So the ideal gas equation, ideal gas equation. The ideal gas equation links three parameters, or three main parameters: the pressure, the volume, and the temperature. So the ideal gas equation is given by PV is equals nRT, where P is the pressure in atmosphere, such that 1 atmosphere is 760 millimeters of mercury. R is 0.082. Atmosphere, dm cube, mole minus 1, Kelvin minus 1. So the pressure should be in atmosphere. The volume should be in dm cube, such that 1 cm cube equals to 1000 dm cube. The temperature should be in Kelvin, such that temperature should be in Kelvin, such that it's temperature in degrees Celsius plus 273. So these are the various conversions. The pressure should be in atmosphere. The volume should be in dm cube. The number of moles, obviously the number of moles. R is a constant, 0.082. T is the temperature in Kelvin. So you can take a typical example. Okay, what is the use of the ideal gas equation here in chemistry? So let's see how we can use the ideal gas equation. The ideal gas equation can be used to determine the molar mass of the organic compound or any compound, if and only if we know the pressure, the volume, and the temperature. So let's take a typical example. Or let's see how we can divide the molar mass. PV is nRT, but N is given mass out of R. molar mass. So we substitute in the ideal gas formula. We're going to have PV equals to given mass, molar mass, RT, such that molar mass equals to MRT over PV. MRT over PV. So the molar mass of the compound can be determined if and only if we have the mass RT PV. So given mass, ideal gas constant, the temperature in Kelvin, the pressure atmosphere, the volume in dmq. So we're going to take an example. In this case, our example will be a GC equation. So take a GC equation. So example, GC equation. Let's look. GC equation. June 2023. The GC equation goes thus. Calculate the molar mass of a volatile liquid if 1.715 gram of the compound occupies a volume of 488 cm cube at 2 atmosphere and 40 degrees Celsius. So the GC equation goes thus: calculate the molar mass of a volatile liquid if 1.715 gram of the compound occupies a volume of 488 cm cube at 22 atmosphere and 40 degrees Celsius. So we're going to remove our data. Remove the data equation. In this case, the given mass have been given to us. Given mass is 1.715 grams. The volume have been given to us in cm cube. So we have to convert the volume from cm cube to dm cube. So the volume would be 488 divided by 1000. Volume equals to 0.488 dm cube. Then the pressure is 2 atmosphere. The temperature is 40 plus 273. So the temperature is 313 Kelvin. 313 Kelvin. So we'll make use of our data. PV equals nRT, but N is given mass out of a molar mass. So PV equals to given mass, molar mass, RT. Molar mass equals to MRT out of PV. MR equals to the molar mass. Calculate the molar mass. So the given mass is 1.715 times R 0.082 times 313 divided by 2 times the volume 0.488. Molar mass MR is 45 grams per mole. 45 grams per mole. So the GC equation is telling us calculate the molar mass of a volatile liquid if 1.715 grams of a compound occupies a volume of 488 cm cube at 2 atmosphere and 40 degrees Celsius. So the mass has been given to us. So the mass is 1.715 gram. The volume has been given to us as 488 cm cube. Then the pressure is 2 atmosphere. The temperature is 40 degrees. So convert from degrees Celsius to Kelvin such that T is equals to 40 plus 273. T is equals to 313 Kelvin. So apply the formula PV equals nRT. But N is given mass while the molar mass. So we substitute in the formula. PV equals to given mass, molar mass, RT. Make molar mass is subject to the formula. So MR equals to MRT all over PV. So we substitute. Our mass, the given mass is 1.715. R is 0.082. So R is ideal gas constant. T is the temperature in Kelvin. P is the pressure in atmosphere. V is the volume. So the molar mass of the volatile liquid MR equals to 45 grams per mole. We clearly see that the ideal gas equation can be used to determine the molar mass of the volatile liquid. So that is the molar mass, the mole concept and equation. So go to lesson 4. Lesson 4 says the mole concept and solution. So go to lesson 4. The mole concept and solution. The mole concept and solution. The mole concept and solution. That will be lesson 4. For the mole concept and solution, we are going to see is divided into 2 parts. The first part, we are going to see how we can calculate the concentration. So, part 1, lesson 4, concentration. So that's part 1 for lesson 4. Concentration.